In our study of plane curves, we want to be able to have a method for finding the slopes of tangent lines for the plane curve. So suppose that we have a plane curve here, given by any point on the curve can be given by, say, x equals f of t, y equals g of t. T is our parameter. The question is, how do we find the slope of the line tangent? To the curve at, say, that point. Well, from our previous study of calculus, we know that the slope of a tangent line is given by the derivative, which we sometimes write dy dx, and we can use the usual method for finding the derivative, or methods for finding the derivative, if we have a rectangular equation which defines our curve. However, if we're given a set of parametric equations, we may or may not have the rectangular equation. So it would be nice to develop a way to find the slope of the tangent line without having to have that rectangular equation. So we go back and think about our idea again. So the way that we got the slopes of tangent lines, if you recall, is we approximated by finding the slope of a secant line. This point, in terms of the parametric equations, could be given by x equals f of t plus delta t, y equals g of t plus delta t. So we changed t a slight amount. That gives us a second point on our curve. And then we draw this secant line in between the 2 points that we have. So we know that the slope of this tangent line that we want is approximately equal to the slope of the secant line. And what we want to do is we want to move this point along this curve closer to this point. And when that happens, the secant line will more closely approximate the tangent line, and so we end up with the slope of the tangent line that we're looking for. So what do we need to do in order to make that happen? Well, we can make delta t get close to 0. How can we do that? Well, let's look again. If we think back and look at just the pictures themselves, remember this picture is actually in the xy coordinate plane. So this distance could be described as delta x, and this distance is described as delta y, the change in y. So delta x would technically be f of t plus delta t minus f of t. That's the change in x. It's the difference between f of t and f of t plus delta t. Notice that if I come in and I divide this by delta t and multiply by delta t, then I haven't really changed that difference any. It's still the same difference, but this now becomes delta x, and f of t plus delta t minus f of t divided by delta t is approximately equal to the derivative of f at t. If you just think of f as being a function of t, this f of t plus delta t minus f of t over delta t, this is the way that we would start out finding the derivative of f with respect to t. We would take the limit as delta t goes to 0, and that would give us the exact derivative. At this point, however, we're not taking that limit. So delta x is approximately equal to the derivative of f at t times delta t. Well, notice that this tells us that delta t is going to get closer to 0 than delta x gets closer to 0. Okay, now how are we going to use this? We said before that the slope of the tangent line is dy dx. That's our derivative of y with respect to x. So let's write that down here and see where we can go. And if you remember back from the definition of the derivative, one way that we could rewrite this is the limit of, as delta x goes to 0, of delta y divided by delta x. Now let's be more specific here. Delta y is equal to, g of t plus delta t minus g of t. Delta x is f of t plus delta t minus f of t. We can see that from our picture above. Delta x is f of t plus delta t minus f of t. Delta y, we didn't write it, but it's the change in y's. So that's g of t plus delta t minus g of t. All right, so we're using that. Now here's the trick that we do. So we're looking for this derivative, the slope of the tangent line. We're going to take our fraction and divide the numerator and denominator by the same quantity. In particular, we're going to divide by delta t. The numerator denominator. So we're taking the limit of this great big huge fraction. But notice if we take the limit of simply the g of t plus delta t minus g of t over delta t, if we were taking the limit as delta t goes to 0, that would turn into the derivative of g with respect to t. And similarly, the denominator, f of t plus delta t minus f of t divided by delta t, would go to the derivative of f with respect to t if we were taking the limit as delta t goes to 0. But unfortunately, we have delta x goes to 0. Aha! Remember, up here, we said that delta t goes to 0 when delta x goes to 0. So we are able to replace our limit. Instead of being delta x going to 0, we may replace it with as delta t goes to 0. So this becomes the limit of g of t plus delta t minus g of t all over delta t divided by f of t plus delta t minus g of t. F of t divided by delta t. Now taking our limits, g of t plus delta t minus g of t over delta t is the same as the derivative of g of t. As delta t goes to 0. The limit of f of t plus delta t minus f of t over delta t is the derivative of f at t. So what does all this mean? Well, if you trace back all of those equations, you can go back and watch again. If you trace back all of the equations, we have the following. The derivative of y with respect to x is equal to the derivative of y with respect to t, the parameter, divided by the derivative of x with respect to t. So this is our method for finding the derivative of a plane curve if we're only given the parametric equations that define the curve. We simply take the derivative of the y-coordinates with respect to t, and we divide that by the derivative of the x-coordinate with respect to t.